Welcome, everybody, to NetApp On Air. As always, I am your host, Nick Howell. Thank you so much for joining us for another episode we are excited about today. Excited to be back. Yes, we've been off for about a month. We've been doing some really crazy stuff getting ready for Insight. We are now less than a month away from NetApp Insight happening here in Vegas at the MGM on September 23rd through the 25th. If you're not registered yet, Drew and I have a special little link over in Discord that we would love if you would use, but make sure you get registered either way. You're not going to want to miss it, and if you're making travel plans, you're going to want to be there for Sunday night because we got a little something special surprise for you, but it's only for registered attendees. You're going to want to be there. We're going to have a little warm-up party on Sunday night, and we're excited about unveiling this for the very first time. We're hoping it's going to become a recurring event, so we're excited about it, but you have to be registered for Insight. You have to be here to hang out with the rest of the community and all of the folks that are coming to Insight from Discord, Reddit, everywhere across the larger NetApp community, and all of you, all of the fans of the show here. So get registered for Insight. Make sure the hotels are filling up, so you got to get cooking before it gets too much later. Insight's going to be fun. We definitely want to see all of you there. We're looking forward to interacting with you. We're going to be doing some special stuff with NetApp On Air that we'll have more information for soon. We'll be getting a lot of that stuff out to you, hopefully within the next week or so. But yes, keep an eye out for everything happening for Insight. We are less than a month away. The best way to keep up with that, as you see the banner going across the screen, join us in Discord. NetAppDiscord.com or discord.gg/NetApp. However you want to get in there. It's like 5,000 people in there now. Practitioners, some of our executives hang out in there. If you want to get some product feedback, all of that stuff, we are in there interacting with you guys all day, every day. So make sure you come and join us in Discord, and it's the best way to keep up with the episodes that are going on here. You can also subscribe over on YouTube, follow us on Twitch, all the socials. It's 2024. You guys know how to do social media at this point. Just make sure you're following us in the places that you would like to follow us. Today we got a good one. We got a really good one because this guy is on my larger team in the office of the CTO, underneath our valiant CTO, Yancey Stephenson. But he is doing some really cool work, and I found out about it recently at the end of July when we had an offsite in RTP, and I was just like, wow, that would be really cool to show how we do some of this stuff to the larger audience here and get it out into the public so people can see it. So let me bring him on. George, welcome to the show, man. Thank you for joining us today.
Hey, Nick. Thanks for having me.
What in the world is going on your whiteboard back there? That looks really interesting, really intriguing.
Oh, I think I was explaining the difference between like access patterns for a spindle hard disk on SATA versus NVMe to one of my buddies.
So it's funny because I saw a meme the other day about the difference between general SSDs or cells versus spinning media.
Yeah.
And when you were telling me about this before the show, that was the first thing I thought of. And that eternal argument that we're always going to have of spinning media or SSDs, which protocol should I use, all that kind of stuff. I don't think that's ever going to go away. But I love seeing a real engineer with a real whiteboard with real conversations happening on it in the background. That's fantastic. So you've been with us for a couple of years now?
Yeah, just about 2 years.
Tell me about your background a little bit. Like, what's where did you come from, and how did you get into doing some of the stuff that we're going to talk about today?
Sure. Yeah, I spent the first 17 years of my career working for federal government and the military. I was a civilian for the military, not in the military.
Right.
But I worked for a couple different commands in Alaska and Germany, and my last 5 years was with USDA in Kansas City.
Nice.
Running virtualization and data centers and lots of storage expertise in NetApp and other companies kind of leading up to it. I just got into, hosting more and more servers and storage and kind of learning how to optimize applications to run in different places and lots of, I guess, tweaking of many different parameters for NetApp and led me to really like the operating system, kind of brought me here.
Isn't it funny how that works? I had the exact same experience where I kind of organically fell in love with ONTAP as a customer. Like it just, there's this organic passion that you get when you figure out all the little bells and whistles and things that it can do. It just, you can't help but fall in love with it. So your boss Chad and I go back 10 to 15 years. How did you find the spot? And I know how he kind of started up the performance engineering side of what his group's doing over there. So I'm curious how you went from working as a civilian in the federal government up to coming and joining NetApp and doing some of the performance engineering work that you guys have been doing.
Yeah, I had actually gotten contacted by a recruiter for like a software engineering manager role. That wasn't really what I was looking for, but I went and kind of was looking at other NetApp jobs and saw this kind of performance architecture, TME type role. And I was like, hey, that sounds kind of interesting. And then I ended up talking to Chad and the recruiter, and it's interesting work to that touches a lot of like different technologies. Like we're not tied to any one cloud provider or any hardware. We really just kind of test the gamut and see like what the art of possible is with different applications. So we get to touch a lot of things, and always interesting and a lot of high impact projects.
Absolutely, and it's you guys are kind of unsung heroes in a way, and I'll sing a little bit of Chad's praises. You may or may not know this stuff, but like Chad is a lot of the reasons that we're successful both in virtualization and cloud. Like he was the guy that we would take all of our performance problems to with like LUN misalignment and all of that stuff 10, 15 years ago. And he had the cube over in the corner. We'd go, Chad, we can't figure this out. Can you figure out why this is, performing so bad? And he would figure it out, and then we'd go fix it in engineering. So like you're in a group, the kind of an elite group, and with an elite dude that knows the ins and outs of storage like really nobody I've ever met before when it comes to that kind of stuff. So now we've seen him do it with cloud and some of the more advanced stuff like what we're going to talk about today with HPC simulation that you've been working on. Like this, guys, this is the stuff that makes storage fast. So I wanted to bring George on today specifically to give you a little behind the scenes of the kind of work that goes into the stuff that we do interoperating with other platforms and other things like that to make ONTAP really sing. And it's not without its stumbling blocks. We've run into things in the past. Before. I brought up the LUN misalignment thing before. Yeah, that was a big detractor, but we're mostly beyond that at this point. But with new workloads, with Kubernetes, with cloud, with AI and beyond, like there's so many, the evolution of HPC, and leading even more into AI, like these are new things, net new things, that hurdles that we're having to overcome. So I'm curious, how'd this project start? If you can give us some backstory before we get into the meat of like what we're going to show here.
Sure. So we had an automotive customer, as well as a couple oil and gas customers in different industries, that had kind of identified one of their challenges or pain points was moving the data into their HPC cluster and then running their HPC jobs and then having to wait to then retransfer it off to where their engineers on their desktops or VDI could actually access that data. And that was a very cumbersome process for them of having to script in some copying out to GPFS or Lustre, something like that, run their jobs and then figure out where the data was eventually written to, and then pull back the pieces that they need so that their engineers could actually do their analysis. So we got brought in and said, we know there's multi-protocol, we know there's flex cache, like would any of these things help some of these workflows? We said, yeah, definitely. We haven't tested some of these applications before, so I don't know how well it's going to perform. And so we worked.
It's kind of a we don't know what we don't know sort of situation.
Exactly. Yeah, it was kind of a big unknown for us. Of these are new applications to us. These are application spaces where a lot of the times ONTAP doesn't play. So we said, okay, well let's try to find some of the ceilings, the limits, see how well it performs, see if it's going to meet these customers' expectations. And then potentially build some solutions and documentation around it.
Fantastic. Let's get into it because at the end of the day, that's what everybody's here to see. I love the setup. I love the journey that you've been on and all of that stuff. But like I helped birth FSX into existence, and I'm curious to see where I think I was at Storage Day when we announced it in 2021. So we're now 3 years. That was 3 years ago. We're also on the 3-year anniversary. We've seen crazy growth in FSX ONTAP. Like I can't even describe the adoption and the growth that it's one of the, if not one of the top 3 fastest growing services in AWS.
I believe
it's crazy to me how much that has taken off. And what it tells me is that there's a void and a hunger for real sort of traditional enterprise storage, reliability, resiliency, and things like that in the cloud, as opposed to just, yet another EBS volume, right? Or yet another S3 bucket. There's something about consolidated unified storage that works in the cloud too. And
Yeah, it is kind of uniquely positioned where it's,
Yeah.
it's a first party service that's sold by Amazon. And you buy it and can deploy it through there, but you can still use the majority of like the core ONTAP features that everybody's really used to, without having to abstract via another API.
Right. And you can even drop down to console, I believe, at the SVM level, right? You can drop down to FSX admin, and like these were all things that we had learned. So FSX, for a little backstory, FSX was like the third version of cloud storage. I loosely call it version of cloud storage because we had done Cloud Volume Service, and we had done that in AWS. And then we came out with Azure NetApp Files in Microsoft Azure, which was like, that was it's kind of a Goldilocks journey, right? Microsoft wanted to do storage arrays. So they're physical arrays that are just, delegated subnets up into the VNets in Azure. Well, Amazon was like, we want to go all the way. We want to just do it ourselves. Like, can we make a version of ONTAP that just runs as a managed service and people can spin up just as easily as an EC2 instance?
Yep.
And it took 2 years of engineering effort, and a lot of that was interop with other AWS services for monitoring, management, spend, any of that kind of stuff. But yeah, it was really fun to see. We won Partner of the Year from AWS for that effort in 2021 when we launched it at reInvent that year. You guys might remember the fun story with the trophy, that me running around Vegas with a trophy at reInvent.
I like it.
Anyway, so I'm going to pull your slides up here because,
Sure.
And yes, we have slides. We're not doing you a presentation of sorts. We needed visual aids to talk through this. But set me up here. How did you come up with this as an option versus using more traditional infrastructure or more traditional HPC simulation styles? How did we get to the point where, was this just a, hey, I wonder if we can do this in the cloud sort of conversation, or was there an intent behind using FSX?
So there was some specific customers we had that wanted to know, really, would this fit for them versus having to use like a traditional parallel file system. So we picked kind of specific technologies that would nearly model what they actually wanted to do in AWS.
Okay.
I'm going to jump into the next slide just as a talking point. So we picked two applications to test with. One was a computational fluid dynamics software that's open source. The link's there for OpenFOAM. And this is similar to some of the other CFD software. There's a Siemens Star CCM Plus is a very popular one, but there's many others that customers use for CFD workloads. And a CFD workload, just for people that aren't familiar with it, I wasn't until about a year ago. That's like if you want to model, say like a motorbike or a car in a wind tunnel, and you want to know what the pressure or airflow is on any part of that bike or any part of the person, how do we compute that? That was one of the examples that they had. It was in the automotive space that they were curious on. And then the other popular software called Radios by Altair. They have an open source version called OpenRadios. And that's a finite element solver. And that's used a lot in you could say like oil and gas, or if you wanted to see, we discussed earlier, the erosion of some land where there's water pressure reducing or increasing. How do we calculate that?
Yeah, I was asking you if I could figure out how it was affected. Lake Mead, we're trying to figure out how much longer Lake Mead's going to last us here in Vegas for water supply.
You could potentially, you can model a lot of things. I wouldn't know how to build that. But if one of those smart scientists or engineers could build it, then I could help them run it.
I went a different engineering route. I went mechanical, electrical. I didn't do the fluid dynamics and stuff like that.
Yeah, it's really math heavy.
Yeah.
So we had picked those two applications, and then we were working with Amazon on this. And Amazon has a really cool project that I wanted to rep a little bit. It's called SOCA, which is Scale Out Computing on AWS. It's a free repo. The link's there for GitHub, and we can throw it in chat or something.
Yeah.
And it's think of it as like a HPC in a box. So you run one command, or you download the repo, run one command, and it'll step you through making a few choices, and it'll deploy everything you need to go submit HPC jobs with dynamically provisioned EC2 instances to actually go run those jobs on.
So is Soka just a Python script or a JSON file that you just kind of import where it and it builds the infrastructure for you?
Yeah, exactly. Yeah, it's a Python script and then a whole lot of Bash and CloudFormation templates.
Okay.
So it deploys like a web interface where people can go log in and submit jobs. They can build VDI desktops for both Linux and Windows from within the web UI or via API or Python. So it deploys all of this for you and just into a couple VMs. It sets up PBS, which is a job scheduler for running HPC jobs. And it also has CloudFormations templates so that when people go submit an HPC job via PBS, it'll go provision the EC2 instances, build them with the image you specify, and then go launch the job immediately. When that job's done, it tears all of that infrastructure down for you. So you're really only having to pay for the compute while those jobs are running.
Good job, AWS Labs. That's fantastic.
Yeah, it's really cool.
Do you find it gets hung or leaves a bunch of stuff behind, or is it pretty clean, pretty good at cleaning itself up?
It's really good at cleaning itself up. I was launching significant amounts of compute during some of these
Can you define
tests.
significant?
So we had, I think the biggest job I did was 2,880 CPU cores for one set of jobs. So it was, I don't know, that's 200 or 240 EC2 instances simultaneously.
Wow.
I hit the upper limit on the account that I was in for instance availability.
That's fantastic. So at the end of the day, this whole thing is more of just like a test bed to run things against. And will it dynamically scale based on the test that you're running, or do you have to sort of modify this based on the test or the simulation that you're running?
So when you submit the job, you specify the type of EC2 instance you want, and then the total number of cores. And then the SOAK application will effectively figure out, okay, how many of those instances am I going to need? And it'll provision that number based off the job parameters.
The number of cores you specified, yeah.
Exactly. Yep. So you could say,
Awesome.
I want a C series and I want 200 cores. It'll spin up, say 6 of them at 32 cores each or something. Or if you want a GPU-enabled one, you could specify a GPU series. It's all very customizable too, and you can make custom templates and add them in. It's all open source, so there's lots of opportunity for modification.
So yeah, before we get into this too much further, like heads up, Drew's putting them in the chat for us. Thank you, Drew, across all the platforms. I look at this as this could be used almost in any way, with any sort of testing that you wanted to do. I think you can even, is possible as well to specify the type of instance. So if you needed GPUs or anything like that, you could specify some of those like M instances or anything that you might want to get into for even larger workloads. If you wanted to do specifically some scale up larger instances within this framework, like you could absolutely blow that out. So how do we get from this to sort of hooking storage up to it? I see you've got 2 different FSX types down at the bottom. Obviously NetApp ONTAP and Lustre. Is that normal? Which one of those you use, is that normally driven by the type of workload you're going to be testing, or how would a user that's unfamiliar with FSX at all sort of pick from the menu of different FSX offerings that are in there?
Yeah, so when we tested, by default in HPC environments in general, people will tend to pick a parallel file system. That's what a lot of academic universities will use. They just default to a parallel file system.
Yeah.
So that's the default that you kind of get when you deploy the SOCA environment. It's going to deploy an FSX Lustre cluster for your Scratch, and then it's going to deploy an FSX Lustre for your actual data storage. So we built a FSX ONTAP instance kind of on the side And then we updated some of the config scripts so that when the CloudFormation templates deploy, we just effectively just ran a mount command to go mount the FSx ONTAP to those instances. So there's a little bit of plumbing to do.
As always. Yeah.
Yep. Yeah. But we wanted both of them kind of there so that we could run, a job on one and then run the same job on the one right next to it, and kind of do a time comparison between the two.
Awesome. So what was the job? Let's get into some of the meat of like what was the job that you were running specifically.
Sure. So we use there's an open benchmarking website that has benchmarks for both OpenFOAM and for Open Radios, and we were using it's called Motorbike, and like I was kind of mentioning before, an example of it's a motorbike in a wind tunnel, and what is the impact of the wind on different pieces of it. So we used a couple different models of that motorbike model. With OpenFOAM, they talk about the number of cells in a model, and that's 100 million or 300 million cells, which is a very, very big model. And then for the Open Radios, we used another one of their benchmarks, which was like a Ford Taurus driving into a pole. And then you can see kind of the impact on different pieces of the car.
Yeah.
I don't have any videos of crashing Ford Tauruses today, but that might have been a good idea.
That would be fun. You do crash test dummy simulations and things like that, right? Yeah.
Yep.
Yeah. Yeah, Drew said in chat, missed opportunity.
Yeah.
Agreed. Absolutely agreed. For sure. Maybe we could circle back to that one day.
Yeah, I think we could. I have the data output, so we could probably put it together and figure out how to visualize it.
Don't tease me. That could be fun.
Yeah, so we kind of picked a couple of these specific tests for say 100 million cell OpenFOAM model with 48 or 72 cores, and then we ran the exact same job with copying the data from FSx ONTAP to Lustre, running the HPC job on Lustre, and then copying it back to where the users could access it on their Windows VDI on FSx ONTAP. And then we'd run the same job with a multi-protocol volume, where the users, they can write their data out, and that can be instantly accessed via NFS from the HPC cluster without having to copy data back and forth between the two file systems. So we measured a lot of different pieces of that to kind of see where is the benefit. Is ONTAP slower for the actual HPC piece, or is it equally as fast as Lustre? And then how much does that copy back and forth actually impact the total engineer's time? So when one of these engineers is having to submit a job, they're waiting until that job is done. So those copy times kind of play into the factor for how long they're having to wait, and really how many jobs that they can do on a daily basis.
Yeah, in parallel simultaneously, or how are their do they need to spin up additional instances if they're wanting to do multiple different parameter runs and things like that? Yeah, so
exactly.
I'm curious, just in general, fundamental differences between Lustre and just a BSD-based operating system like ONTAP. Like I'm trying to think of like what can we help the users understand about why you would choose one over the other. I can sit here and sing the praises of ONTAP all day. I will admit I've never used Lustre. I've never put it into practice in anything, so I'm ignorant. So I'm wondering if you can share, like, what are some of the pros and cons of both? Are there reasons to choose one over the other? Technically, obviously, we're NetApp, so we want everybody to use FSx ONTAP, right?
Yeah.
But transparently, like, is there reasons somebody would choose FSx Lustre over FSx ONTAP for a specific reason?
There is. I mean, they have the very different designs. So ONTAP we run in HA pairs, and workloads can be either on one node, or we have some technologies like flex groups with PNFS where you can kind of distribute the load across many nodes. Parallel file systems like Lustre or GPFS or BGFS, they're parallel in nature to where when you send a request, you're talking to like a metadata server that then tells you where to go read or where to write those files to.
Yeah.
So the scale is very different, where you can have 100 storage servers behind a Lustre file system that are all working in parallel to handle your disk I/O. And so they scale very differently.
Yeah.
Lustre has its own file system, its own storage client on the Linux hosts, and that works really well for some of these very large parallel environments where you're needing, say, 100 gigabytes a second of throughput for a single namespace.
Where does it fall on his face would be my question. Like, where does it start to, fall apart on you? And you look at something a little bit more like FSX ONTAP.
Yeah, it's really it's really fast and parallel, but it's not, I'll say, feature rich.
Yeah.
So we don't have things like dedupe in Lustre. You don't have things like flex clones or flex cache or tiering cold data to object. Like, it's just not as feature rich because it's designed for a different purpose.
Yeah. Good point. Okay. You want to get into some of the testing and talk us through like what some of your findings were and all of that stuff? Is that what's next?
So I have two charts to show kind of. So when we're looking at the job runtime, I wanted to see, okay, how much is actually copying the data at the end of the job. So this is when I ran a 100 million cell job on Lustre, and we can kind of see that this whole area on the left side. This is just looking at the destination storage where I was copying the data to. So during this, we had I/O on the Lustre system where it's writing checkpoints, reading some data. But if we look at this, it's about an hour total job time.
Okay.
And this last 10-ish minutes was essentially just the job's done, but now I'm having to copy the data from Lustre out to somewhere where the user can access it on their Windows VDI.
Explain that for me. Like, what does that mean? Like, where is it copying from and to in this instance?
So in this instance, it's copying from the Lustre file system that the HPC cluster has access to.
Okay.
And it's copying to either an FSX ONTAP with an SMB share, or it could even be an EBS volume that's attached directly to a VDI instance.
So there's no way for the engineers to access the system directly, is kind of what you're saying.
Yeah, so a lot of these applications...
It would have to be copied off somewhere else.
Yeah. A lot of the applications that some of the customers are using are Windows applications, or they're used to using the Windows version of those applications.
Right.
And Windows just can't speak Lustre, especially a Windows desktop or Windows VDI is never going to speak to a Lustre file system directly. So you might have a 50 or 100 gigabyte result set or data set that you then need to get to that engineer's desktop or to at least a share where that engineer can access it. And that's what this big copy piece is taking it from the Lustre file system that the HPC kind of crunch those numbers on, and then getting it to somewhere where the engineer can actually go run some analysis and view the results of the car crash.
But it's not writing the first megabyte until the job is done running. So
exactly.
It's not able to do those operations sort of simultaneously as the job is running. It has to wait for the whole job, then it writes it off.
Yeah, in this scenario, this is kind of how some of that might be able to be scheduled with some fancy scripting of like some sort of file system detection and then copying data off as it starts coming in. But the scripts we used for kind of the standard benchmarks for OpenFOAM were really let the job run, and then at the end of the job, then copy the data off. Most of the data that you have kind of during the run is like checkpoint data, or there's probably some other terminology for it that is like, if one of the cores fails, then I need a place to go restart. So we really,
so it's doing it all in parallel across multiple cores, the 2,000 cores that you stood up, right?
Yeah, exactly. It uses a thing called MPI or OpenMPI to kind of distribute that work across all of the different cores.
Yeah. So this is doing 100 million on Lustre, running an OpenFOAM simulation.
Yep. So this is what it looks like.
This looks very different. So
this is kind of some of the I/O that we would see. So this orange is the write I/O.
Okay.
So we see it. It does a bunch of reads at the front, and then it's doing these checkpoints and writing the results sets out at different increments. And we would have seen similar type patterns on the Lustre file system from the last chart. But we see at the end when the job is finished and it's written that last checkpoint out, it's just done. We don't need to go then copy that data off so that the engineer could access it. So like when it's done this last write, that data is accessible via the engineer on their desktop now.
So for the NetApp admins listening in and watching, translate that into Flex and Snap words and how ONTAP is actually enabling this, because I'm curious as well how the hell we went from what you showed before to this with the exact same 100 million OpenFOAM job just because we're using a different storage backend. I'm seeing heavy reads at the very beginning. Is that it's loading it into the file system?
Exactly.
Okay.
Yep.
And then it's processing all of it in these little chunks. This is the same kind of 1 hour time span I'm looking at as well, roughly,
Yep.
right? So I'm seeing, I want to understand in Flex and Snap words, I guess, is the way I'd describe it. Like how in the world we did this versus what we just saw on Lustre, which you would think would be more a superior kind of parallel file system to do a 100 million job. This is very shocking.
Yeah, it's really just the ability to create a multi-protocol share. So we have, in this example, we have the share exposed via both NFS and then also SMB, and that's one of the fairly unique things to ONTAP in the FSX world is that you can have both of them accessed directly. HPC nodes, they're all Linux. They really just speak NFS or Lustre for custom file systems for Linux. Windows, you're going to be using an SMB share, or if you were EBS, that's going to be like a locally attached disk.
I mean, if you're a sadist, you can use NFS on Windows, but I would do not recommend.
Yeah, I haven't seen that work out too well for a lot of people. It works. It's just there's some big limitations there.
Yeah.
But yeah, it's really multi-protocol is the big piece for this. The other things you mentioned, like using flex clones and snapshots and fabric flex cache.
Flex cache.
Those all definitely play, and I'll actually talk about flex cache in a little bit. I just don't want to sidetrack myself yet.
So for comparison's sakes, go back one slide for me real quick, and let's really dial this in. And I'm sorry if I'm being pedantic here, but I'm really trying to make sure that I drill home the difference in these two things. On one side of it, we have to wait for the entire job to finish, and then we have to take the results of that job and do a full one-to-one copy of it off to another instance or another volume that can be shared and accessible by Windows desktops engineers. All right?
Exactly.
If we go to the next slide, we're looking at the exact same job being run on a storage backend that can share both natively, and the result of that is near instant access to the data as it's being processed.
Yep.
And we're seeing no huge reads because it's all available as the job's being processed. Almost it's real-time accessible. Is that the right way to describe it?
Yeah, I think that's a great way to describe it. Is as soon as it's written from a Linux client, you can go read the same data from a Windows client without having to do any sort of transforms or copies.
Wow. I mean, it's amazing how something that simple as having a multi-protocol setup that's accessible from two different things can just fundamentally change how you operate on a day-to-day basis. And, we went back to, we were saying at the beginning how you organically fall in love with ONTAP as a customer. This was literally the reason why I fell in love with ONTAP, guys. When I bought my first, I had never heard Network Appliance or NetApp or anything back in the mid-2000s, but we bought one at the behest of CDW to put VMs on. And we bought it. The only thing it was doing was block, and the only thing it was doing was holding VMFS data stores.
Yeah.
That's it. What I stumbled backwards over my heels into is, we can put all our home drives and departmental shares, and we can point net back up to this thing, and then we can snap mirror it over to another one in a colo facility, and like the way that's how a lot of this stuff kind of happens. I love seeing this exact same story play out in the cloud with FSX ONTAP.
Yeah, I kind of started it, the reverse way. Is I started with NetApp using it for primarily file shares like home drives. And then we were like, wait, we can do iSCSI from this too.
Mm-hmm.
We can
and fiber channel.
Yeah, and fiber channel, and we can like not have to have the separate block appliance for these these VMDKs, and then just kind of ran with it.
Yeah. This is amazing kind of stuff. It's funny. I'm having a bit of a deja vu moment because I hear this kind of story from NetApp customers over and over and over and over again, and just swap out the different contexts that they're experiencing it in. This example, you're doing HPC simulations in the cloud with ONTAP. I experienced it through virtualization and managing day-to-day operations in a data center 15 years ago, 18 years ago. People finding how to do it with Kubernetes and using S3 repos to pull in Helm charts to deploy and provision nodes and containers and stuff in their Kubernetes-based environments. The story remains the same, and it's just ONTAP everywhere.
Yeah,
It's really what it comes down to, man. The
Yeah.
more you have it sort of universal across your system, it doesn't matter if it's in AWS or on an all-flash FAS or if it's on a FAS. ONTAP is ONTAP is ONTAP is ONTAP. And it's going to enable this kind of functionality to the point that it just becomes about port count. How many cables can you plug in? How many nodes can you scale it to?
Yeah. FSx
So-
ONTAP I think scales to 24 nodes now. That's a massive cluster.
That was in December of last year, I believe we announced that was coming at
Yeah, I think
reInvent
so.
last year. So it's been almost a year now.
Yeah.
No, 9 months since then. So who knows what we're going to talk about at reInvent this year? I know. But I'm not
Yeah.
going to tell anybody now. Big trouble.
Yep. So to put some
yeah.
kind of numbers on what you were asking about for like why does this matter?
Yeah. Good call out there, John. One intelligent data infrastructure to rule them all. That's it, man. Hashtag ONTAP everywhere.
Yep.
Okay, this is where we're getting into some of the meat of this. We were just looking at the graphs of these, but talk me through what all these numbers are and how they apply to like the graphs we were just looking at.
Sure. So the graphs that we were looking at previously, so the first graph was kind of over here on this Lustre section. So the simulation time, this is how long did the actual HPC job take to run. So this is 2,742 seconds in that example. The total time, including that copy at the front and at the end, was 3,300 seconds.
Okay.
And so that's an extra almost 10 minutes from the engineer's perspective. So this total time column is really kind of what the engineer from the automotive customer was concerned with. Is the simulation time is important. I mean, that's how long you're having to pay for the compute nodes.
Yeah.
But you're also having to wait for all of this copy back and forth so that they can actually do something with the data.
Well, you made a good point there. I want to call out.
Sure.
So the combination of the SOCA test bed, and then when you're running 10 minutes at this scale, could mean millions, right? Of spend in AWS. So if you're doing this to the scale of like 10,000 nodes and you're doing GPU simulation type stuff, if you're building the metaverse.
Yeah.
You could be talking about millions of dollars in 10 minutes. So it is that 10 minutes might not sound like a lot to those of us that are just managing file shares for our corporate office, but in the world where, and that's important. I'm not trying to belittle that because that's what I did. That's what I started with. But I'm saying that this, in the world of cloud, 10 minutes is an eternity, and it could really, really damage your invoice that you get every month.
Yeah, for a lot of these customers, the compute and storage costs versus the licensing costs that they have to pay like per core, and then the engineer time can be even the most expensive resource for them.
Yeah.
So we can save on both the infrastructure costs of how long they're having to pay for the compute, and then more importantly for some of the customers is we're saving their engineer time and letting them run that next simulation based off the results of the previous one even faster.
Without having to take 10, 15, 20 minutes and going and making a sandwich. You just move right on to the next one.
Yep. And so in the middle section, we then compare, how long was the total simulation time and the total time. And some of these numbers, like this includes like provisioning the EC2 instances and some other pieces. But
so the simulation time seems to be the same.
Yeah. So on some of the smaller models, the simulation time was almost identical. There is some instances where the actual simulation time was faster on Lustre.
Okay.
But the total time that the engineer was having to wait was reduced in some of those scenarios. It depends on the workload. It depends on how large these checkpoints are, how large the files are, and then also like what SKU you're using for your FSX or your Lustre file system, or sorry, your FSX ONTAP or your FSX Lustre file systems. There's a lot of tunables and a lot of parameters in these that you can tweak as you need, and scale on demand if you need. Like we used a fairly small both Lustre instance and FSX instance for a lot of these tests, so that we didn't have to spend a significant amount of money for testing for weeks on end. But these are just example numbers in a couple different scenarios.
Yeah. So it does seem Lustre performs better on the sim itself because of the parallel nature of the file system underneath. But overall, we're seeing a massive difference in time saved, accessibility. What other ility words can I think of? Like there's a lot of moving parts to this.
Right.
And Darth's trolling me. I want to address it. I want to see how much it costs you to run a data center that can host 2,800 cores and the related storage systems underneath it, and show me that power bill at the end of the month. And
with that level of on-demand flexibility.
Right, exactly. Right.
Yeah. Yeah, and that's an interesting point. Like, there's nothing stopping you from having a lot of this on-prem, and then just bursting these workloads. Like when you need 2,000 extra cores, just spin up an FSX ONTAP instance in AWS, set up a flex cache between the two, and then scale that flex cache up and down as you deploy HPC nodes.
You could even do a separate flex cache for different departments. If you were like running different simulations against the same data set, like you can design this in a way that is super simple, super efficient. You don't have to copy a bunch of data off to different places, all kinds of stuff. There's all kinds of reasons. All the flex and snap words, guys. That's the key here. Yeah,
actually, I have a slide kind of. This is something some of our EDA customers really like is they'll burst, like depending on when the region is. When they can get like spot instances in a region that's really cheap, is they'll spin up a flex cache, clone some data, and then just run their HPC jobs, and then you can have a persistent flex cache out there at the minimum SKU size, like say 128 meg or 256 meg SKU, and then go burst that up to a 4 gig SKU if you want to run some HPC jobs, and then scale it back down. Those are the great things that give you that type of flexibility, that if you're doing that on-prem, you're buying that infrastructure. If you're not always going to use it, that can waste some dollars.
But it's also an argument to potentially repurpose some gear as well. If you do have some workloads that get moved to the cloud that end up evacuating some on-prem gear, you could repurpose that for a test bed.
Yeah.
Like, it's kind of the same way we would repurpose stuff as we would do refreshes and things over the years. Like, you can find things to do with that storage. It's probably still good enough to run some of these benchmarks against. Is it going to be the top tier, bleeding edge, super duper daddy performance? No. But depending on what you got laying around, you might can make use of it, even if it's just to serve a flex cache up to FSX.
Yeah.
And so don't sleep on. So Darth, I wasn't trying to call you out intentionally there, even though I kind of was, but this is different than trying to do it on-prem. You're certainly possible. It's not something I would personally want to take on because you're managing a secondary facility almost to production, because this is all for testing and simulation stuff. This is where we get into the conversations about digital twins and that kind of stuff. That's where these conversations typically lead to. So like 5 years out from now, like there's a lot of companies that are doing digital twin stuff already, especially manufacturing. They're trying to find efficiencies on the lines and in the robotics and things like that. But like 5 years from now, we're making digital twins of entire cities at this point. Go and look at some of the projects that the city of Boston is doing right now. It's fantastic the way that they're trying to modernize a lot of that stuff. But how do we go from this to something that I feel like something like SOCA and other things that are built-in test beds like that what we enable with FSX, with SOCA, is the ability to kind of build your own, bring your own digital twin in a way, where you can simulate these kinds of runs and see what it would look like to do that. And I know AWS has that native service for doing it's was it starts with an I. I can't remember the name of it off the top of my head. But it's I would be curious to see how those two compare. And I see Taylor's over in the chat. We can probably bring Taylor on at some point. Tim Riggins, as I call him, and talk about some
AWS
of stuff.
has they have like AWS Parallel Cluster, and they have quite a few other services to kind of go run a lot of this for you. This is if you want like a fully self-managed kind of HPC in a box type scenario.
IoT Twin Maker. That's okay. What I had to go look it up. But yeah, that was launched at reInvent in 21, I believe. I remember that.
Very cool.
But I remember things like that. I remember Twin Maker really standing out to me as, whoa, that's going to be really cool in a few years. And then AI sort of took the world by storm over the last couple of years. But this kind of stuff right here, I think, is where more realistic existing NetApp customers today that have existing core infrastructure that they use, and maybe they're still running production out of the on-prem kit, but they want to be able to do some unit testing. They want to be able to do some simulations. They want to be able to, try to build some models or something like that around all of the corporate data that they have in their production. Snapshot Flex Cache.
Yep.
And run the SOCA script, spin it up, run whatever you want against it, tear it all down, get a bill at the end of the month. That's almost impossible to reproduce on-prem. That flexibility.
It is. If they already are scheduling jobs on-prem, like they don't have to use SOCA. They can use a lot of that same methodology of just spin up EC2 instances and connect them to FSXN. They can you can build that all yourself, or even steal scripts from the SOCA repo.
Yeah.
There's nothing proprietary about it.
All right, let's see if we got any other questions. All right, did you have any other slides diagrams you wanted to show?
So I had one other talking about like kind of an example of when I had mentioned just a little bit earlier about like when do you need to scale? I had one scenario where I was running I want to say 30 or 100 simultaneous jobs. So I kicked off jobs like at the same time, and so all of them kind of read in at the same time, and then they all started writing their checkpoints at the same time.
Okay.
And so this is, I know it's kind of a messy chart, but earlier when we saw that FSXN slide where the checkpoints writes were like a very narrow peak.
Yeah.
This one is an example where my checkpoints were almost half of the actual runtime. And so this is just to highlight that this is an example where the storage SKU that I had deployed at the time was really choking the compute. To where I had say 100 servers deployed. Those 100 servers are spending half of their time waiting on disk. So they're trying to write their files out, but there's a throughput cap for a 1 gig SKU or something. And so this is an example where like if I would have known before like how much write throughput I was going to try to push through, is I would have then scaled up or scaled out to multiple nodes.
Yeah, so you're up over a gigabyte per second here.
Yeah, exactly. Yeah.
Which is a lot.
Yeah, it is. Yeah. And
I said gigabyte, not gigabit.
Yeah. So 8 gigabit.
Yeah.
This was many, like 30 or 100 parallel jobs running at exactly the same time. Where, most of the time multiple people are going to be submitting them, or they're going to be, delayed, and even just a few seconds between them would have helped in this case. But monitoring your storage is important. Like you'll get reports from some of the HPC software that shows like how much time they actually spend on things like waiting on I/O. And anytime waiting on I/O is we're not doing math on the CPUs or GPUs.
Yeah. I'm looking at this going, okay, so you have this and this happens to you. Do you have to tear it all down and rebuild it larger, or how do you remediate a situation like this?
So in this scenario, I was using a mid-sized FSX on ONTAP instance, and I could have scaled that up on demand and just said, okay, I want to, instead of using a 1 or a 2 gig SKU, I want a 6 gig SKU is I think what our ceiling is right now. If I was going to be doing more and more of that, I could have scaled out to say 4 6 gig SKUs and multiplied my write throughput by a factor of n.
Damn.
Yeah, so lots of flexibility, but thought this
So
might be
the one thing that I noticed, there's a lot of reads at the end of that. Well, I say a lot, but there's more than 0.
yeah.
I'm seeing a steady read line there. Where is that coming from? Do you remember from the run?
I don't remember off the top of my head what that little bit of reads was.
Because all of the FSX ONTAP charts were really read heavy up front, and then you barely saw any the rest of the way through. But I'm curious what that little hump is there at the end.
Yeah, I'd have to go back and look at logs. That could have been.
It's probably an errant thing or whatever.
Yeah.
Well, cool, man. Where do you go from here? I guess to wrap up the show, like, what's next after you make this discovery? Like, what's the next thing you want to test? What's the next thing you want to see it break? Is there a next on the list beyond what you've learned doing this?
Yeah. So now that I'm more comfortable, I guess, with some of the technologies that are used in the HPC field, like MPI for running jobs, individual jobs across many compute nodes. I've done that on CPUs. I want to see kind of how we can take the same thing and scale out to GPUs and some different some MLAI training or even fine tuning type scenarios, and how well do those perform, and then where's kind of our thresholds for upper ceiling on those type of applications.
Yeah, any training or like inferencing jobs, stuff like that. I'm really I'm curious about how that would work. I'm curious to see how GPU workloads would work. Yep. I'm going to throw that up there because he's saying the same thing. Nucky Duck, thank you for the question. You took the words out of my mouth. How does this transition into model training with GPU workloads? Things like that.
Yep.
For these kinds of simulations. I'd love to see that if I can plant a bug in your head. Put in an official request. Does this same
we're working on it.
Does this same outcome hold true? Right? Do we see similar results just with different computorial methods versus CPU versus GPU? Do we see the same sort of behavior? I guess is the way that I would word it.
Yeah, I'm interested. There's some I guess context in there that because the GPUs are so much more expensive.
Yeah.
How does that kind of play into our factor of how much does those copy times at the front and the end really matter as much?
Bingo.
And so that's things like where we have fit up to. If people are doing some fine tuning, like is that where we're a good fit? Is training some of these massive models? It's things that I want to find out. Kind of where can we play in there, and where are some of our benefits, gonna outweigh, kind of the traditional methods that people are using.
Well, make me a promise. When you do get all of that work done, you'll come back on the show. And
I will.
We'll go back over it because I'm invested now in this journey. I'm invested in seeing where this goes. And just like Nucky Duck just said a second ago, I want to see this with GPU instances too.
Yeah.
We all know AI is all the rage right now, but we're really at NetApp, we're really focusing on RAG and how sort of corporate customers retrieval augmented generation, for those that aren't aware of it, and how the customers are taking existing data sets that they have on their NetApp systems and being able to process those and use those to train models for their own internal systems, for their own internal employees to use their own internal data. And there's some companies have decades of data in archives and backups and databases and all this stuff. And that's the big thing right now for us specifically, because most of our customers are corporate enterprise customers. They're the ones that have very large systems, decades worth of data, and they're going to be doing some of these model trainings very soon, if not already. So I would be curious to see how you take some of the stuff that you just showed today and do those models and simulations and training in the cloud, doing maybe some RAG workload.
Yeah.
Inferencing would be really stressful on a CPU GPU setup, especially GPUs.
It definitely is. Inferencing isn't quite as storage heavy in a lot of the cases where you're really just loading a model in. But RAG is is where you start to hit disk a little bit more, and we're definitely going to have some interesting things coming up for that soon.
Fantastic. Well, George, thanks again for being here today. This was fantastic. Guys, if you have any questions, George hangs out in our Discord, so make sure to jump in there and hit him up. So we got lots of stuff going on. George, I got a few closing thoughts. Thank you very much for joining us today. Come hang out in the Discord with us. I'm sure people will have follow-up questions with you, and we'll see you back next time for some more info on GPUs and stuff like that.
Yep. Sounds good. Thanks for having me, Nick.
All right. Thanks, George. All right, guys, there we go. I hope you guys enjoyed that one. We got a little geeky, got a little deep on that one. And that's my lane. That's where I love to be. I don't want to spew a bunch of marketing stuff at you guys, even though I do sometimes, which I have to market that Insight's coming up here at the end of September, on September 23rd through 25th. You're not going to want to miss it. We're doing a community warm-up party on Sunday, September 22nd, the night before. So it's the first one. I've been trying to get it together for 5 years. Thanks, COVID. We finally got it off the ground. It's going to be happening Sunday evenings, but you got to be registered. You got to have your badge. So make sure you're registered. Make sure you get to the show in person. We're going to be doing some other things for everybody else. More details soon. Hint, hint, wink, wink. I can't talk about them just yet, but yes, John. Boots and pearl snaps, absolutely. Bring your S kickers and your pearl snaps and your 10-gallon hats, because it's going to be a good time. Once you register, official invites will be going out next week. If you are registered, you will get an invite, but you have to be registered. So make sure you get in there and get registered. It's going to be a good time, guys. Make sure you don't miss this year. We've got a lot going on, and Drew and I have worked extensively hard to make community a core fundamental pillar of the entire event. So there's going to be a lot of things going on at Insight this year that is for you, right? Of course, we're going to have our keynotes. We're going to have our messaging. We're going to have all of our launches and announcements and all that stuff. But Drew and I have worked really hard to bring ONAIR to the show, to get the community warm-up party going, the PIN programs back. You're going to see all of this stuff, right? If you go to insight.netapp.com, you can see all the speakers. You get all the sessions. Schedule Builder is out for those of you that are registered. Like, everything's out there at this point. We're less than a month away. So don't miss out. This is going to be a fun time this year. And hope you guys can make it, because we'll be seeing you there. But until next time, my name's Nick Howell. Thank you so much for joining us. I really appreciate it. And we'll see you guys next week. Take care.